Stop signs, facial recognition, autonomous drones. Our world is built on the confidence of artificial intelligence. But what if I told you there's an invisible, almost magical weapon that can break these billion-dollar systems with a single pixel or a cheap sticker? To the human eye, this is a picture of a Panda Shutterstock. But watch what happens when we change its digital structure with a tiny, imperceptible layer of noise. The AI, with 99.9% confidence, now sees a Gibbon. This isn't a software glitch. It's a profound vulnerability called an adversarial attack, and its real-world consequences are terrifying. A few pieces of tape can turn a stop sign into a speed limit sign for a self-driving car, or a special pattern printed on a t-shirt can make you invisible to surveillance cameras. The core evidence is clear. Our AI systems, for all their power, have a massive, easily exploitable blind spot. To understand the fix, you need to understand the problem. Why does AI see a panda when we see a gibbon? Humans recognize objects by their high-level features. The shape of the ears, the black and white pattern. AI, especially deep learning models, doesn't see that way. It looks for statistical patterns and low-level features, tiny, hidden correlations between pixels. We can visualize this process using a concept called gradient descent. Think of AI's confidence as a landscape. The AI's job is to place the input, the image, into the deepest valley, the correct category. An adversarial attack simply calculates the steepest path out of the correct Panda Valley and into the wrong Gibbon Valley. It adds the minimum amount of noise, the single pixel change, needed to tip the AI over the boundary, landing it in a completely different wrong conclusion. The change is too small for our biological eyes to process, but it's a massive signal in the statistical space the AI operates in. These attacks aren't theoretical hacks in a lab. They are real security threats, fitting into two main categories. First, evasion attacks. This is the Panda to Gibbon trick. It's about deceiving a trained model during its use. The stakes are huge. Imagine facial recognition used at an airport being fooled by a specific pair of glasses to misidentify a terrorist as a known celebrity. Or a voice assistant getting a silent audio command buried in music that tells it to unlock the front door or browse to evil.com. Second is poisoning attacks. This is where hackers contaminate the training data itself. Before the model is even deployed, a hacker can introduce a few malicious, mislabeled examples, creating a secret backdoor trigger. For example, they could train a security system so that it correctly flags a virus 99% of the time. But if the virus file has a secret, tiny tag hidden inside its code, the system is programmed to confidently label it as safe. We need the evidence engine to not just detect these attacks, but to prevent them. So, how do we build an AI that can't be tricked? We use a cutting-edge technique called adversarial training. This is how we create robust models. In simple terms, it's like an AI immune system. Instead of just showing the AI clean, correct pictures of pandas, we intentionally show it its own vulnerabilities. We feed the model millions of adversarial examples, the exact images with the pixel noise, and tell the AI, "This still a panda. Learn to ignore the noise." We force the model to look past the small statistical tricks and concentrate on the true high-level features that humans use, fundamentally changing how it perceives the world. This process is computationally intense, making the model take longer to train, but the payoff is an AI that is resilient, trustworthy, and resistant to these subtle, calculated manipulations. The evidence we provide the AI is not just the data, but the proof of its own fallibility. Adversarial attacks expose a profound truth. As AI takes over critical systems, its security is a matter of public safety. We've shown you how effortlessly a machine can be tricked, but also the scientific breakthrough, adversarial training, that allows us to fight back and build evidence-based, robust AI. By forcing our models to confront their own weaknesses, we don't just secure them, we make them genuinely smarter. The future depends on systems we can trust, and that trust is built on security.